Hello everyone, welcome back to another video for the series. I'm Inokyu, and today I brought a very exciting problem from PUMaC. I think it stands for Princeton University Math Competition. Um, I think as you might know, so if you have been watching my series, I think you might know that these days I haven't solved many competition problems because I have KMO in less than 40 days, so I need to practice more Olympiad style problems, like proof based problems. But I actually tried this problem because it was like a some kind of assignment. It was a problem from an assignment from our school's math team, and um, as a person who is obsessed in math, I love our math team, and I also love the problems that they give us. So that's why I had to try. I just tried this problem, and it took me a whole 30 minutes to come up with an original solution. So the solution that I'm going to share today is not uploaded anywhere in the internet, I believe. So if you think I made a mistake, or if you think my solution is not complete, please feel free to share that in the comment below. Then, without further ado, let's start. Also, the reason why I just provided the diagrams is because uh, I actually coded them, and with the help of technology, I was able to get these diagrams. But uh, the reason why I put it here is to to give a basic idea on how our diagram should look like when I draw it by hand. And uh, I think it's not fun to have like pre-written, pre-drawn diagram. So let's start with our hand, because that's what I did when I first solved this problem. So triangle ABC has angle A equals 90 degrees, AB 2 and AC 4. So we have triangle ABC. Like this, I guess. BC, and this is 2 and this is 4. Circle omega sub 1 has center C and radius CA. So it should look something like this. Oh my goodness. Guess this is not bad. Oh no, that's way off. Okay, so let me try that again. So I think like my tip on drawing is I'm not good at drawing, so I just have to say these kind of things. So just draw like 4 dots and then try connecting them. I think that helped me when I first drew the diagram for this problem. I mean, yeah, I'm not the one to say this because just look at my diagram. It's a perfect circle right here. Now, I don't think it really matters, because what matters the most is logic, not like the diagram. So anyhow, here is my diagram right here, like this. Oh, that's so bad, but okay. We could, oh yeah, we can adjust them. Yes, I think I'm starting to get a good shape on like yes. So the two circles intersect at point E. Different from point A, so this point is E. Point M is on omega sub 2, so this is omega sub 2 in the interior of ABC, so it should be here somewhere, such that BM is parallel to EC. So if EC, our EC like this. It's parallel, so oh no, that was good. Yeah, so this is M right here. Suppose, oops, yeah, so think I got it. Yeah. So suppose EM intersects Umiasa 1 at point K. So we're going to draw EM like this. And this point right here is K. So this point right here is K. And AM intersects this point right here is Z. What is the area of quadrilateral ZEBK? Like this. Yeah, I think my diagram is not bad right now. I'm pretty satisfied. Also, I'm not planning to like rigorously write each step because like I don't think we really need to be rigorous. I mean, we do need to be rigorous here, but we don't have to write it rigorously. Like we don't have to write, I would say, not like formal proofs, but we don't have to be that formal because we don't have to submit our proofs here. So let's start with basic observations. So the first thing that I noticed is since triangle ABC, like this triangle right here, is a right triangle, BEC must also be a right triangle like this. So this angle right here is right angle. And the reason is because EC is same as AC because it's a radius of omega sub 1. And AB and BE are the same because they are the radius of omega sub 2. And they also share BC, so by SSS congruence, triangle ABC and ABC and EBC are congruent. I will just write them. So angle ABC is congruent, triangle ABC, so EBC. Yeah. After that, what I noticed is I just wanted to chase few angles because I thought that would provide some useful and helpful information. So notice that if you just say that this angle right here is alpha, this angle is also alpha. And that's because triangle BME, this is an isosceles triangle. They share the same BM and BE because it's a radius. And also, by construction, BM and EC, they're parallel to each other. So, meaning, this angle right here is alpha. And because alpha plus alpha is 90 degrees, alpha equals 45 degrees. I thought that was quite nice here because like 45 is not bad. Yeah. And then I spent my next 10 minutes trying to think of what I should do next. And I think, yes, it's quite hard to see from here, but we should actually, yeah, so the one thing that I wanted to prove was the K, C, and Z are collinear. So the point C, like the center of the circle, is actually on the line, on the segment KZ. meaning KZ is the diameter. And the reason why I wanted to prove that is because if we actually prove that, then I think we could actually find the area, because we can find the area of KEZ. So that was the first thing that came to my mind. So I wrote a lemma that KCZ are collinear, and started. So how I proved it is, we know that EC is same as KC because it's a radius. So we're not looking at KZ right now. We're looking at a new line like KC here, like this. We're only looking at this. We're not. We don't know yet if they're collinear or not. So by looking at KEC, we know that this part with red segment is also alpha here, and that's because isosceles triangle, meaning this angle right here is right angle. Therefore, it suffices to show that CZ is perpendicular to EC. Then automatically, KC and CZ will form a straight line. So we want to show that this is right angle right now. That means we want to show that this part is 45 degrees. So that if this is 45 degrees, then this should be 45 degrees because isosceles triangle, and we prove it. So let's prove that this part, this angle right here is 45 degrees. And there is something that I wanted to do here, and I just chased the other angle. So let's say that this part is, I will say, no, I will not state it. Let's use triangles ACZ. Let's use triangle ACZ. If we use triangle ACZ, notice that we can use triangle ACZ because A, M, and Z are collinear by construction. So this is an isosceles triangle. So this angle and the angle formed by AZ or AM, they're equal to each other. Now let's look at this angle right here. If you look at this angle, this is actually the same as for this angle, let's consider the chord AE. So based on chord AE, we know that because C is the center of the circle, ACE is twice the angle of AZE. That's like what we learned in school. So 2 theta and this is theta. So I just use this property, and using that we get this 2 blue. But because I said because we know that triangle ABC and triangle EBC are congruent to each other, this is 2 blue, and each angles, so ACB and BCE are blue and blue. So we can say that without loss of generality, let's just use this one. No, I don't think it's right to say without loss of generality here, but let's just use this one so that we can actually utilize this triangle right here. So angle EZC is blue plus green, but blue plus green, let's just say that this is red. Blue plus green is red, and so this angle is the same as this angle because, yeah, just look at this triangle right here. Now let's look more closely at the red one. And I was actually very happy when I saw this because there's one thing that I really wanted to use, and that's radical axis. So we know that AE is the radical axis of omega sub 1. So AE is the line AE is the radical axis of omega sub 1 and omega sub 2. That means BC and AE are perpendicular to each other like this. We could actually prove that, but wait, I think I proved this in my... No. Yes, I didn't prove this property, but I did something similar in my previous videos, so please check that out if you're interested. Anyways, because we know that this is 90 degrees, if we prove that, so I just want it to be optimistic. So if we prove that, is there a new color? I'll say let's use yellow. I want yellow. If we prove that this yellow right here is 45 degrees, then we prove that this angle is 45 degrees. So we somehow need to prove that I'm sorry, let's use different color. I can't see yellow. I love purple. So we just need to prove that this purple angle is 45 degrees. That way, we know that the red one is 45 degrees because it should be 45 degrees, and we prove our lemma. So how do we prove that this is 45 degrees? And we are also doing something similar here, and this time let's consider the chord EM. If you consider the chord EM here, then we know that where's the center? EM, this angle is 2 purple. How should I say it? 2 purple, like this. If this is dot. We use the same property that I just described here. And notice that because 2 purple is 90 degrees, because 2 purple plus alpha equals 180, alpha plus alpha is 90 because they're 45 degrees. 2 purple is equal to 90 degrees. So this is 90 degrees, like this. That's why purple is 45 degrees, and we proved our lemma. So we could know that K, C, Z are collinear. Now we're done because we know that ZEBK, the area of this quadrilateral, is the same as the area of triangle ZEBK. So this is the same as, let's split them, triangle EBK plus the area of triangle EBK and KEZ. Yes. So this is equal to EBK is equal to, let's use our favorite formula, 1/2. This is 2 times this EK is 4√2 because this is 4, and it's right angle right here, times sine alpha, which is this, plus what is KEZ. Now this is where you could actually apply or use our lemma. So KCZ are collinear. That means the area of this is simply KZ times EC. Yes, because it's also 90 degrees. So it is 1/2 times 8 times 4. So this is equal to, we cross them out, cross these out, so we have 4 plus 16, which is 20. And that is indeed our answer. So I think this problem was like a very fun problem for me because we could actually, so I just like chasing angles because I think they're interesting and fun. But this problem was interesting in a way that chasing angles and somehow using our radical axis right here helped us solve the problem. So I was when I first tried this problem, I was trying to use the power of point theorem because I think I think that's like what we should try, because we see AMMZ and EMMK. But I didn't find that to be really helpful because even though the area is related to length, so I was trying to like somehow utilize those properties and like try using like cyclic quadrilateral or use like Heron's formula. But I realized that those are like quite unnecessary, because by chasing angles we can gain more information. And the sole reason why I started tracing angles is to get more information, like the fact that K, C, C are collinear. So I learned a lot from this problem. I really enjoyed solving this one too. So if you also enjoyed this problem, please don't forget to like and subscribe. And uh, tomorrow I'll come back with another very fun and interesting problem. Thank you, and see you tomorrow. Bye.